Hello guys, and welcome once more to this new video into our YouTube channel. So in today's video we are going to be solving the advanced level Westmore further mathematics paper 3 2022 actually. So we are going to be solving question 4, and this question was on radial and transverse motion of a particle. The question is, the radial and transverse components of the velocity of a particle at the point r theta are 2r squared and 3 theta squared respectively. Initially r equals 1 and theta equals 1. A. Show that the polar equation of the part of the particle at time t is r squared equals 3 theta divided by 4 minus theta. B. Show that the radial component of the acceleration of the particle at time t is 8r raised to the power 4 minus 9 theta raised to the power 4 divided by 4, and find in terms of r and theta the transverse component of the acceleration of the particle. Let's actually launch into the solution of this question. That is, let us first of all solve the A part of the question. That is, let us show that the polar equation of the part of the particle at time t is r squared equals 3 theta divided by 4 minus theta. We know that the r the t can still be written as the r the theta times the theta the t actually. Yes, it can still be written like this. Why? Because you calculate that the theta in the numerator can cancel the theta in the denominator, from which you are still going to be left with the r dt, and the r dt actually corresponds to r dot. We calculate that what the theta dt corresponds to theta dot, for which the r dt is therefore going to be equals to the r d theta times theta dot, okay, which actually is equals to r dot actually. So this is what we are going to use in order for us to prove that the polar equation of the part of the particle at time t is this actually. So we need theta dot and we need r dot, for which once we are going to have those values, we are therefore going to obtain the value of r in terms of theta by separating variables, and after which we are going to integrate both sides actually. Okay, it is following those steps that we are going to obtain this required proof actually. We know that the velocity of a particle, okay, is given by two components, that is the radial component of the velocity and the transverse component of the velocity. The radial component of the velocity, okay, is given as r dot, and the transverse component of the velocity is given as r theta dot actually. For which you can therefore get what we can therefore write it as what r dot to be equals to 2r squared, because in the question we are given 2r squared to be the radial component of the velocity of the particle actually, and r theta dot to be equals to 3 theta squared, because in the question we are given 3 theta squared to be the transverse component of the velocity of the particle actually, for which we already have r dot. It just left for us to obtain actually theta dot actually simply. Yes, but we know that r dot equals to the r theta times theta dot. Clearly at this level, as I told you, we are going to obtain the value of theta dot and r dot, from which we are going to put in this equation, and after which we are going to separate variables and integrate both sides for us actually to get the expression of r in terms of theta actually. We can place it out from this expression, that is r theta dot equals 3 theta squared. We can obtain the value of theta dot, okay, that is theta dot is therefore going to be equals to 3 theta squared divided by r actually. Okay, yes, and remember we already have r dot and we have theta dot. We can therefore come out of those two values here and actually get the value of r in terms of theta, that is by separating variables, and after which we are going to integrate both sides actually. Yes, so we know that what it implies, this equation, that is r dot equals the r theta times theta dot, is therefore going to be equals to what? 2r squared, because r dot is actually 2r squared. Okay, it's actually going to be equals to the r the theta then times theta dot. Theta dot is 3 theta squared divided by r actually. Yes, for which at this level we are simply going to do what? First simplifying, we are going to obtain the r the theta to be equals to 2r cubed divided by 3 theta squared, for which you can therefore separate variables. Separating variables, we are going to obtain the r divided by 2r cubed to be equals to the theta divided by 3 theta squared actually. Yes, for which if we integrate then both sides, we are going to obtain this, that's the integral of the r divided by 2r cubed to be equals to the integral of the theta divided by 3 theta squared actually. Integrating that, we are going to obtain a negative 1 divided by 4r squared, that's the integral which is on the left hand side, to be equals to negative 1 divided by 3 theta plus, that is this one is corresponds to the answer once we integrate this right hand side, this right hand side actually, plus therefore the constant of integration. We have therefore to obtain this constant of integration. How then can we obtain this constant of integration? We have to take note of these initial conditions which are given to us. That is, initially we are given r to be equals to 1 and theta to be equals to 1 as well, so we can obtain the constant of integration from from those initial conditions. That is, substituting the value of r, which is equals to 1, and theta equals to 1 into this expression, we are going to obtain negative 1 quarter to be equals to negative 1 third plus k, from which you therefore get the expression of k, that is the constant of integration, actually 1 divided by 12 actually, from which this expression, that is negative 1 divided by 4r squared equals negative 1 divided by 2 theta plus k, is therefore going to be equals to negative 1 divided by 4r squared, okay, equals negative 1 divided by 3 theta, then plus 1 divided by 12. 1 divided by 12 is the constant of integration, which actually obtained here actually. Okay, yes. So if we multiply both sides by negative 4, we are going to obtain 1 divided by r squared to be equals to 4 divided by 3 theta, then minus 1 divided by 3. Remember, I multiply, okay, both sides of this equation by negative 4 actually. I obtain this actually. For which, if you further simplify, we are going to obtain what? If you do the LCM on the right hand side, we are going to obtain 1 divided by r squared to be equals to 4 minus theta divided by 3 theta actually. Yes, for which you therefore obtain the value of r squared to be equals to 3 theta divided by 4 minus theta. It's actually that required that is that required polar equation of the part of the particle at time t, which we are actually required to prove actually. Yes. Okay, let us actually move into the B part of the equation actually. That is, let us show that the radial component of the acceleration of the particle at time t is 8r raised to the power 4 minus 9 theta raised to the power 4 divided by r, and find in terms of r and theta the transverse component of the acceleration of the particle actually. Yes, actually we know actually that the acceleration of the particle consists of two components, that is the radial component of the acceleration, which is r dot dot minus r theta dot squared, and the transverse component of the acceleration, which is actually r theta dot dot plus 2r dot theta dot actually. So we are first of all going to start by solving the first part of the equation. That is, we are first of all going to show that the radial component of the acceleration of the particle is this, and after which we are going to find in terms of r and theta the transverse component of the acceleration of the particle. So saying that, it implies that what? Since we want to show the radial component of the acceleration of the particle at time t is 8r raised to the power minus 9 theta raised to the power divided by r, it simply means we are going to show that this expression, that is r dot dot minus r theta dot squared, which is actually the radial component of the acceleration, okay, we are going to show that this expression actually is equal to this actually, because that is what is being asked actually in the equation actually. Saying that, it implies we can therefore write the radial component of acceleration of the particle to be actually equals to r dot dot minus r theta dot squared actually. Okay, yes. Once we can further write it as what? We can write it as, that is the radial component of the acceleration as what? As d open bracket, that is r dot dot, okay, can be written as d open bracket the r dt, then the theta, then times the theta dt, then minus this r theta dot squared. So if we look it more closer, we are going to, okay, realize that what? If we look it much more closer, okay, we are going to realize that what? If we cancel, if this theta and this other one cancels, actually we are going to be left with d open bracket dr dt, then divided by dt actually, and this expression actually corresponds to r dot actually. So this expression corresponds to r dot actually. So writing this whole expression is that we are simply writing dr dot dt actually correspond actually to r dot dot actually. Yes, so this whole expression, it simply means the r dot dt, and this corresponds actually to r dot dot actually. So writing all of this also implies r dot dot actually, it is still valid, okay, and you have to take note of this very important, okay, expression for r dot dot actually. Okay, for this, once you know this actually, you are going to easily, okay, come out with your different calculations as far as radial and transverse motion of a particle. For this is a very important expression, okay, and I explained to people how actually, okay, it is linked to this one actually. As I said, this whole expression is simply the r dot dt, and which actually corresponds to r dot dot actually. Okay, then minus, therefore include this other term, that is minus r theta dot squared actually. Yes, so we actually know that what, but r dot actually equals 3 theta squared. If you remember, r dot, which is what, which is the transverse component of the velocity of the particle, okay, was given to the equation, it was given the equation to be 3 theta squared. Once you can therefore get the expression for theta dot, okay, and theta dot, which is actually equals to 3 theta squared divided by r, and we obtain therefore the expression for theta dot squared, because remember we want to obtain this expression in the first place actually. So theta dot squared actually is going to be 9 theta raised to the power 4 divided by r squared actually. Yes, for which you can therefore, okay, obtain, we are therefore going to obtain the radial component of acceleration to be equals to d, open bracket, the r dt with respect to theta, that is the theta, then times the theta dt minus r, what is theta dot squared. Theta dot squared is actually this expression, which is 9 theta raised to the power 4 divided by r squared. For which, further simplifying, actually we are going to obtain what, the radial component of acceleration to be equals to d r dot, remember this interior term actually, that is the r, the theta is actually r dot, then the theta, then times the theta dt minus 1 r is going to cancel with 1, this r is going to cancel with 1 r in the denominator, from which you are going to be left with minus 9 theta raised to the power 4 divided by r actually. Yes, from which, further simplifying, we are going to obtain the radial component of the acceleration to be equals to d. Remember, this r dot corresponds to what? This r dot corresponds to the radial component of the velocity of the particle, which was given to be 2r squared in the equation actually. Okay, yes, so saying that it implies the expression therefore for the radial component of the acceleration is therefore going to be d, open bracket, 2r squared the theta, then times the theta dt minus 9 theta raised to the power 4 divided by r. But we know that r squared equals to 3 theta divided by 4 minus theta. We proved this actually. We proved it, if you remember actually, which was the polar the polar equation of the path. Okay, the polar equation of the path actually of the particle, which we proved actually in the first part of the equation actually. So we know that r squared equals to that, this expression, that is r squared equals 2 theta divided by 4 minus theta. So if we come and substitute this expression here, what are we going to get? We are going to obtain therefore the radial component of the acceleration to be equals to d. Okay, remember 3, this r squared, if you multiply this 2 here, we are going to obtain 2 times 3 times theta, which is actually 6 theta. So I've simply multiplied 2 times the expression of r squared, and I obtain finally that the radial component of the acceleration, the particle, actually equals to d, open bracket, 6 theta divided by 4 minus theta d theta, then times the theta dt actually corresponds to theta dot, then minus 9 theta raised to the power 4 divided by r actually. For which you can clearly see that what, this expression is in terms of theta, and we are differentiating with respect to theta. So we are simply going to differentiate it normally as we know actually by applying the quotient rule. If you see it closer, we are going to apply the quotient rule because this expression depends on theta, and actually we want to differentiate with respect to theta actually. So saying that it implies the radial component of the acceleration is going to be equal to, differentiating this one using the quotient rule, we are going to obtain 4 minus theta, 4 minus theta, then times 6 minus 6 theta, then times negative 1 divided by 4 minus theta squared. Remember, we simply apply the vu prime minus uv prime divided by v squared actually, quotient rule actually, where u is the term which is up and v is the term which is down actually. Okay, yes, then times theta dot. What is theta dot? Theta dot is actually 3 theta squared divided by r actually, that is theta dot, then minus 9 theta raised to the power 4 divided by r actually. Yes, from which, if further simplified, we are going to obtain therefore the radial component of the acceleration, okay, to be equals to 24, that is 6 times 4 actually, we get 24, then minus 6 theta plus 6 theta divided by 4 minus theta, okay, squared, then times 3 theta squared, okay, divided by r minus 9 theta raised to the power 4 divided by r actually. Okay, yes, from which we had this expression, that is the radial component of acceleration. The radial component of the acceleration is actually equals to 24 minus 6 theta, okay, then plus 6 theta divided by 4 minus theta squared, then times 3 theta squared divided by r minus 9 theta, okay, raised to the power 4 divided by r actually. This is what we had, okay, for the previous slide actually. Yes, in which if we further simplify, we're going to clearly see that what this 6, this negative 6, okay, negative 6 theta plus 6 theta gives us 0 actually, which are going to be left with what, the radial component of acceleration to be equals to 24, okay, divided by 4 minus theta squared, then times 3 theta squared divided by r minus 9 theta raised to the power 4 divided by r actually. Okay, from which, if we look it more closer, if we bring the theta squared, okay, together with this 4 minus theta squared, actually we are going to have what? We are going to have this expression, that is the radial component of acceleration is therefore going to be equals to theta divided by 4 minus theta, all that squared. Remember, I simply brought this theta squared together with 4 minus theta squared actually, and this 24 I simply multiply it with 3 for me to get actually 72 divided by r here actually. Okay, then times, of course, theta divided by 4 minus theta all squared, then minus this other expression, that is minus 4 theta raised to the power 4 divided by r actually. Okay, but remember, if you see it much closer once again, you are going to realize what this inner expression actually corresponds to what? Correspond to r squared, correspond to r squared divided by 3. Why? Because if we obtain, actually, let me just indicate it. Why? Because we obtain, okay, if you still remember, we obtain the expression, okay, we had this expression in the first program we proved. We had this expression which was actually what? 3 theta, okay, then divided by 4 minus theta. Actually, we can clearly see that what, if we want to get theta divided by 4 minus theta, that is, if we divide all through by 3, we are going to realize that what, if we want, we are going to divide this expression by 3 and this other one by 3, that is, if we divide this other, also divide here by 3. Excuse me if my writing is not so good. If you divide it by 3, you are going to get this 3 is going to cancel this other 3 actually, from which the expression theta divided by 4 minus theta is going to give us r squared divided by 3 actually. Okay, reason why I have this here, that is theta divided by 4 minus theta corresponds to r squared divided by 3 actually, which I have proved here actually. Yes, good. So actually from which we are therefore going to obtain this expression actually, that the radial component of the acceleration is going to be equal to r squared divided by 3 all squared, then times 72 divided by r minus 9 theta raised to the power 4 divided by r actually. Okay, for which, if you look it more closely, you are going to realize that what the radial component of the acceleration is going to give us what? If you look it more kindly closer, you are going to realize that what this r here we are going to have what? We are going to have r raised to the power 4 divided by 9 actually, but r raised to the power 4, the r is just down is going to cancel with 1 r up. We are going to be left with r raised to the power 3. Then in the denominator we have 9 here. Remember, 9 goes here 1 time, 9 goes here 8 times actually. Reason why at this level we are going to obtain 8r cubed, then minus 9 theta raised to the power 4 divided by r actually. Good. From which, further simplifying, we are going to obtain this expression, that is the radial component of the acceleration of the particle to be 8r raised to the power 4 minus 9 theta raised to the power 4 divided by r actually. This is actually what was being required for us to prove, that is the radial component of the acceleration of the particle at time t is 8r raised to the power 4 minus 9 theta raised to the power 4 divided by r actually. Yes. So we have already answered the first part of the question actually. Nice. Let us move into the next part of the question, that is, let us then find, in terms of r and theta, the transverse component of the acceleration of the particle actually. Remember that what the transverse component of the acceleration of the particle is given by r dot dot plus 2r dot theta dot. Remember, very important, that is the radial component, the transverse component, the transverse component of the acceleration of the particle is given by r theta dot dot plus 2r dot theta dot actually. Yes. If we look it more closer again, as I said, theta dot dot, okay, if you remember, in this expression, that is, if we replace theta dot dot with this big expression, I'm going to as well explain how actually we got there actually. That is, if we do same for the case where we had r dot dot, it's the same stuff here, okay, but instead of everywhere we had instead the r, we are going to replace with the theta. Everywhere we had the theta, we are going to replace with the r. Why? Because you can clearly see that what this expression cancel with this other one actually. We are going to be left with d open bracket the theta the t, then divided by the t actually, and this inner expression corresponds to theta. Excuse me if I'm not writing much closer, just actually Okay, get what I'm saying? This inner expression corresponds to theta dot. This inner expression here corresponds to theta dot. Actually, excuse me if I'm not writing very well. Yes, this inner expression corresponds to theta dot. So this expression, this bigger expression, actually is going to be d theta dot dt, and it actually corresponds to theta dot dot. I hope you are seeing that. Good, because if we cancel this one, this term, you're going to be left with d open bracket the theta dt, then divided by dt, and this expression corresponds to theta dot. So finally, here we are going to have what? D theta dot dt, and this actually corresponds to theta dot dot. Actually, yes. So as well, take note of this. Take note of this very important expression for theta dot dot. Very important. Actually, okay, good. When you can therefore further write the transverse component of acceleration to be equals to r. Then, as I said, this expression is actually theta dot, then the r times this expression here corresponds to r dot. Okay, good. That is r times d. This expression here actually is what? Theta dot. So I'm going to have the theta dot dr, then times the r dt, actually, which is actually r dot, then plus 2r dot theta dot. Okay, good. So we don't know what, but we know that theta dot equals to 3 theta squared divided by r, and actually r dot as well is equals to 2r squared. We got the expression from the we were given this initially in the first part of the equation. Actually, yes. So if you substitute those values here, you are going to obtain the transverse component of the acceleration to be equals to r, then times the theta. You're going to obtain the transverse component of the result to be r, then times the theta r, then times the theta dot dr. We are simply going to differentiate this expression with respect to r. Actually, doing that, we're going to obtain minus 3 theta squared divided by r squared. If we differentiate this expression, okay, with respect to r, actually we get this expression. Then times r dot is actually 2r squared. Actually, yes, it's 2r squared. Then plus 2r dot is 2r squared. Then times theta dot is 3 theta squared divided by r. Actually, from which, further simplifying, we are going to obtain the transverse component of the acceleration to be equals to negative 3r theta squared, then plus 12r theta squared, for which you therefore get the transverse component of the acceleration, okay, of the particle in terms of r and theta to be equals to 9r theta squared. Actually, and this actually what we get. That is the expression that is, it therefore answers the next part of the question, that is we are to find where we are asked to find in terms of r and theta the transverse component of the acceleration of the particle, and actually we have it, that is the transverse component of the acceleration of a particle in terms of r and theta. Actually, so thank you very much for watching this video, and remain tuned for very next interesting video. Actually, so don't forget to like, okay, to subscribe to the YouTube channel if you have not yet done so, and put on your notification so that once I'm going to upload a new video, you should benefit from it. Actually, so thank you very much for watching this video, and remain tuned for very next interesting video. Bye bye.